Hello everyone, welcome to Mech 3313 Thermo-Fluids Lab at UTEP. This is your instructor Naushad Arslan Islam, and today we'll be going over viscosity. In this experiment, we're going to be covering viscosity measurement of fluids. To do that, we need some fundamentals on viscosity, Newton's law of viscosity, types of viscosity, importance of viscosity. We're going to be also covering some applications and factors affecting viscosity and some measuring methods for viscosity. Once we know these, we can go ahead and do our experiment. So what is viscosity? Viscosity is basically resistance to fluid flow. To be more precise, viscosity refers to internal friction between moving fluids. That is the friction between each layer of fluids while it's moving. You can also say it as the intermolecular friction between molecules and creating resistance to flow. It can also be resistance from fluid to an adjacent fluid or fluid to an adjacent solid surface. Um, Viscosity can also be defined as the resistance to gradual deformation from or to the fluid from outside force or a shear force or a tensile force. It is usually denoted by Greek letter mu, and the unit is in SI, Pascal second, and the English unit is pound for second per meter square. Newton's law of viscosity. So Newton was the very first person to relate shear stress and shear rate with viscosity, and he said that they are linearly proportional to each other. Shear rate and shear stress change linearly. Um, Assume a quick flow where the bottom plate would be stationary and the top plate would be moving with the velocity u. If you don't know, a quick flow is flow between two plates. So if the top plate is moving with velocity u, the fluid adjacent to it also be moving with velocity u. Now that would create a velocity gradient, as you can see on the right hand side pictures. Now from that you can see that the force acting on the top plate would be proportional to the velocity of the plate u and the area of the plate in contact with the fluid, that is A, and it would be inversely proportional to the distance between the top and the bottom plate. So the force is F would be proportional to AU divided by Y. Now, to equal it, Newton assumed a constant that he took as mu. So the mu is called the coefficient of viscosity for Newtonian fluids. Now, if you assume the force per area is stress, then F over A would be, in this case, is shear stress, tau. So tau would be equals to mu u divided by y. If the if the if the velocity change gradient with displacement is not constant, and if it varies, then you can write that as delta u divided by delta y. This is called as shear strain rate or velocity gradient. You can call it both. Now then tau becomes equal to mu delta u delta y, which is basically called viscosity or absolute viscosity for Newtonian fluids. Now, there's two types of fluids, Newtonian fluids and non-Newtonian fluids. The Newtonian fluids are those that behave uh, as a linear manner when plotted in the shear stress versus shear strain plot. So it show a linear relationship like the one showed in the middle on the plot. Examples of Newtonian fluids are usually air, water, glycerin, alcohol. Most liquids are Newtonian fluids. However, there are fluids, those are non-Newtonian fluids, which do not follow these linear relationships. They used to deviate from um, the linear relationship. Those are called non-Newtonian fluids, and you can see there's they can either be shear thinning or shear thickening. What it means that the viscosity could be either less or more depending on um, the fluid. Suppose printer ink would be shear thinning, whereas paints, asphalt, glue would be shear thickening. So these are all examples of non-Newtonian fluids. Now, types of viscosity. Although we were talking about viscosity to be termed as mu, there are actually two types of viscosity. One is called absolute viscosity, the other one is called kinematic viscosity. The absolute viscosity is just the resistance to flow and is denoted by mu, and the equation is tau equals to mu d delta u divided by delta y. The SI unit is Pascal second or Newton second per meter square. The English unit is pound force second divided by feet square. However, kinematic viscosity is basically resistance to flow under influence of gravity. This is basically um, viscosity normalized by velocity. Um, so this is also given as the ratio of dynamic viscosity to density, and it's denoted by Greek letter nu. So nu equals mu divided by rho. The SI unit of this would be meters square per second, and the English unit would be feet square per second. Factors affecting viscosity. The major factor that affects viscosity is temperature. You see, in case of liquids, as you increase the temperature, the viscosity will decrease because as you increase temperature, the molecules inside the liquid starts to go further and further apart. So the viscosity would decrease. In case of gas, the viscosity would increase with increasing temperature. Why is that? Because even if you increase the temperature of a gas, the molecules are already further apart and they do not have that much effect between uh, them for increasing the temperature. However, when you increase the temperature, since they're very far apart, the molecules heat up and they gain kinetic energy, and that results in them impacting with other molecules, and uh, that increases your viscosity. Now, for pressure, though, increasing pressure does not change the viscosity too much in gases. However, when in case of liquids, if the liquid is operating at a very high pressure, increasing viscosity would increase the viscosity of the liquid. Increasing pressure would increase the viscosity of the liquid. Because in this case, when you are going to be um, putting pressure on the liquid, you'd be bringing the liquid molecules more closer to each other, and that increases your viscosity. Now, why is viscosity so important? Well, viscosity is generally important for a lot of reasons. Suppose heat generation. Inside your car engine, you have um, engine oil that reduces the wear and tear between the moving parts. So if you don't know the viscosity or how viscous your engine oil you need to stop that wear and tear, you'd wreck your car. Uh, then again, if two viscous surfaces mates with each other and starts rubbing, they would they would produce a lot of heat. Again, the viscosity is required to know how much energy you need to um, use your pump to lift water to a certain height. Viscosity would help you to understand boundary flow inside pipes, and it would also help you characterize flow over external bodies. And these are just some of the examples. Why is it important? There's a whole lot many fluid mechanics aspects where viscosity is really needed. So this is very important to actually understand how viscosity works. Applications. Now, for viscosity, there are a whole lot of applications. I already mentioned some important. Why is it important? Now, in case of applications, you can see in petroleum industry, I already spoke about the engine oil. So if you wanted to use the engine oil, you need to know the viscosity. If you wanted to pump something, you need to know the viscosity so you can understand how much losses you would have on the pipelines. If you're if you're harnessing gasoline from underground or natural gas or oil, liquid oil from underground, you need to know the viscosity so you can know how much head you require, how much suction pressure you require to pull that oil up. Viscosity is also required if you're raising pumps to elevate fluid from one height to another height. Depending on viscosity, you need different power, different settings, different systems of pump to get your fluid to a desired level. In case of cosmetics, the fluid flow and feelings can be understood from viscosity. In medical applications, they use viscosity to find proteins. Reynolds number, that is basically one key aspect of fluid mechanics, where you use viscosity to identify whether flow is laminar or turbulent, which is very, very important in case of understanding how flow would behave, or will it create disturbances in your uh, component or not? How efficient your fluid flow would be? All those things. Viscosity measuring method. So there are quite a few viscosity measuring methods, but we'll be talking about generally four viscosity measuring methods here. The first one would be Zane cup viscosity measure. Well, this is used in Israeli paint industry, where they use a cup which have a small hole at the bottom, and they'll put the paint in there, and they'll see how much time it requires for the cup to get empty. Um, so from those that discharge rate from the hole, they would actually relate it to viscosity using some empirical equation. The other method is called falling sphere viscometer or viscosity measuring method. In this, you're going to use a steel ball and put it uh, through the fluid at terminal velocity. The rate at which the velocity would drop as it sinks into the fluid would be used to actually measure the viscosity. The rate of the velocity drop is actually related to Stokes' law to find the viscosity in this case. You can see the equation where it says how the viscosity is measured. In this case, eta is termed as viscosity. This method is usually used in ships to actually find out the quality of fuel going to the ship's engine. Another method would be vibrational viscometer. This method is widely used in process applications in industries. So in this method, you'd have a vibrator or two vibrators immersed in the fluid. Once it is immersed, the vibrators would start vibrating and create a damping force. Now, an electromagnet would pick up the resonating wavelengths, and the displacement sensor would be used to actually measure the displacement or the damping displacement. Now, the higher the viscosity would be, the higher would be the energy exerted, and higher would be the damping force to keep the wavelength resonating at the same pace. And the displacement sensor would actually relate it with the wavelength to actually get your viscosity. The final method is the rotary viscometer. This is usually used in quality controls in industries. This actually involves two cylinders where one would be stationary and the other cylinder would spin. The viscosity is going to be measured by the torque differential between them. You can see a viscometer, rotary viscometer on the picture. In this case, instead of two cylinders, there's one for keeping the fluid in a cylindrical cup or a cylindrical device, and there's a styre which would be the one that will be spinning. And you can see the calculation where the force from the force equation, you can see that the rotational velocity and the cylindrical area is used to actually relate it to the torque and then find out the viscosity of the component. In our experiment, we're going to be using one just like this, a rotary viscometer. The details of that viscometer and the experimental procedure of the viscometer and the viscosity experiment would be actually uh, discussed in detail in the class. Um, for the online part, this is what I have. Um, if you have questions, please note them down and do ask me in class. And thank you for listening.